All right, it's week 3, and we are going to move on to gas stoichiometry. Now, this is going to be a little bit different than the regular stoichiometry we did last chapter, but not a lot. Part of it will seem like it's a little more difficult, a little bit more hoops to jump through, but part of it will seem even easier than what it was. Basically, it's exactly the same thing. Remember, stoichiometry is the science of measurement, and we use the equations on the board just out of your vision. Hopefully you have them on your formula list. And you won't really get any new formulas, but you might want to take some stuff down so that you can follow along. We're going to do some problems. I will cut away and do some demonstrations so that you can actually see this in action, and hopefully it will make more sense when you can visualize it. I enjoy this part. This would be a lot more fun if you guys were here to jump along with me, but luckily I will be off camera when the reactions happen, so you will not get the pleasure of seeing your teacher jump, even though he knows what's going to happen. But in gas stoichiometry, the problems are going to look very similar, but instead of just moles and mass, most of the time in gases, we talk about volume. Sometimes we talk about weight in grams, but most of the time it's going to be volume with gas. So an example like this is just simple propane, and just like you would use if you're camping and you've got a camp stove with one of the green containers there, and you screw it on. When you combine that with oxygen, you burn it, you produce carbon dioxide and water, and that's why you see natural gas, that any hydrocarbon like this, methane, propane, butane, all of those theoretically produce only carbon dioxide and water. Would be very, very clean burning. Now, we talked about percent yield in the last chapter. Not all of it goes completely to carbon dioxide and water. Unfortunately, there's some partial products that come along. So we have some carbon monoxide. We have some other unburned just carbon that's out there. So there's some others. It's not as clean as what it seems, but that's why they're trying to move towards those clean burning hydrocarbons. It's still better than what we have. It's just that we don't have the cars set up to use them yet. So it's probably a ways in the future. All right, and it tells us that this reaction takes place at 45 degrees Celsius and 745 torr. How many grams of propane are required to produce 100 liters of carbon dioxide? Now, we talk about grams of the propane because it's a liquid. We can't talk about the volume because then we'd have to get into the density at 45 degrees. What is the mass divided by volume, and we could figure out what the volume is. But when it's a liquid, we don't really care. Liquids and solids, we talk about masses. When we talk about gases, then we talk about volume. So it says the reaction takes place at 45 degrees and 745 torr. So we're looking, this is our desired. And our given is carbon dioxide. Just like last chapter, we've got to turn the given into moles. Now, before we took the mass divided by molecular weight, and a lot of students still try and take, well, I'm just going to take 100 divided by, and I know what carbon dioxide is, that's 44.01 grams per mole. But it doesn't make any sense to take the volume and divide it by the molecular weight. That gets liters per grams per mole, or liter moles per gram, which doesn't make any sense at all. If it's a gas and it's in volume, we have to use the ideal gas law. Ideal gas law, remember, and I'll write it up here just so we have it, is PV equals nRT. And the N is the number of moles. So we just have to solve this for moles. And hopefully you have them on your formula list. N equals PV over RT, and that will equal the moles. So I can take the pressure, 745, times the volume, which is 100, divided by the R, and since this is in torr, it's going to be 62.396, times the temperature. And the temperature of 45 degrees Celsius, you have to add the 273, is going to be 318 Kelvin. So I'm not even going to get out my calculator and put the numbers into this, because I don't really care what this number is, but that's the moles. That's how many moles I have to begin with, times the desired over given, 1. No, I haven't balanced it yet. I see. Okay, so is this going to be one of the fun ones? 3 and 4, maybe not. Okay, so I need 3 of these. Let me do this in case I have to change it. 3, that balances that, and I need 4 of these. And that gives me 3 times 2 is 6, plus 4 gives me 10 oxygen, so I just need 5 of those. All right, so now my desired over given. Desired is 1 over the 3 times how many grams of propane are required. All right, and now I will grab my calculator. That's not one that I have memorized. 3 carbon or 36.03 plus 8 hydrogens, which is 8.064, equals 4.094. Okay, so that's not any different than what we did before. Just before, we would have turned it into moles by taking mass divided by molecular weight times desired over given times the molecular weight of the desired. So it's exactly the same. So our answer, I'll work backwards. .396 times 318. If you're keeping score at home, 2, 3, 3, and this actually will be 3 because I'm going to add plus 273 and we go by the place. So I'll get 3 significant digits equals 55.2 grams. The only difference is we turned this into moles using the ideal gas law, and then we did the stoichiometry. Otherwise, it's exactly the same. For the second one, we'll use the same equation. Oh, I should have kept it balanced. Let's see, we did 5, 3, 4. Yes. It takes place at 45 degrees and 745 torr again. What volume of oxygen is required to produce 36 liters of water? Now this is going to look like it's going to be a lot more complicated. It's really not going to be. This is one of those, like in math and sometimes in science, where it gets to be really messy and it cleans up pretty easy. So if we start out with this, and we're going to say, let's see, what volume of O2? So here is our desired, and our given is water. So we're going to turn our given 36 liters at this and this, those two conditions, we're going to turn them into moles. And a lot of times, just for convenience and consistency, they'll just say the reaction takes place at STP. They're still giving you the same information. They're still giving you the pressure and the temperature, it's just standard temperature and pressure, which most of you were, I think all of you got on the last one. That's just 1 atmosphere or 760 torr and 0 degrees Celsius. So let's turn this into moles. And again, remember, N equals PV over RT. So the pressure is 745. And I'm going to write out the units this time. It will make it look a little messier, but it will, you'll see why when we're done. Times 36 liters. I'll skip the significant digit knowing that it's actually 3. Divided by 62.396 times temperature, which is the 318 Kelvin. Now times desired over given. And we're looking for oxygen, so it's times 5 over 4. And then that will give me moles, but it's asking for volume. So now I have to turn this into volume. Volume equals nRT over P. I think you have that on yours as well. It's just the same equation, just putting the P down here and the RT up there, just doing a little bit of algebra on it. So now I've got to take it, I've already got the N. The N is what I have out of all of this is the N. So times the R, 62.396, times the temperature, which is 318 Kelvin, divided by the pressure, which is 745 torr. And this isn't just this problem. In gases, as long as the reactants and the products are at the same conditions, this will happen. Look at, I can do a little algebra here too. 745 on the top, 745 on the bottom. 62.396 on the top and on the bottom. 318 on the top, or on the bottom, I'm sorry, and on the top, so they cancel out. And I'm left with 36 times desired over given will give me my new volume. So as long as the conditions are the same, you can take volume times desired over given will equal the new volume. So all I need to do on this one is just 36 times 5 divided by 4 equals 45 liters. So it looks like it's going to be kind of tricky, but it's not. In gases, if you're going from gas to gas, conditions are the same. It's just volume times desired over given will give you a new volume. Doesn't matter if you're on the same side. If I was going to say if this much is produced, how much water is produced, I could just do the volume of this times desired over given, and that will give me the volume of that, as long as they're both gases. Doesn't work if one of them is a liquid or a solid. Now, we aren't going to go into this because not that you aren't up to it, not that you're not capable of it. It's one of those things that it's just a whole lot easier if I'm here and I can walk you through a couple of them rather than you coming back and just watching the same video. And believe me, I've watched them. I know that this is not something that's going to make you want to rewatch it over and over again. So I'm going to show you how to do this because it will probably come up if you're in chemistry in college, and I don't know that you're going to be, that you're not going to be. I want to make sure you're prepared in case you are. Like I said on the last one, we can do this easy thing if they are at the same conditions. If they're not, it's not horrible, but then we just have to do this whole thing here, and this is an example. So now it says the reaction takes place at 45 degrees and 745 torr. Same thing we've had, but the products are vented at a higher temperature and a lower pressure. Why would they do that? They do that because that would force, now this is not a industrially good, equation, we are not going to try and produce water and carbon dioxide. But if you were making something, sulfuric acid, if you were making something and it was produced as a gas and then condensed down, sometimes it can go this direction, but the reaction can also go back the other direction. And if it did, you sometimes change the product conditions so that it's driven this way, and very little of it is going to go back the other way, because that's you're losing money. That's costing you if your product is turning back into your reactants. You don't want that. You want it all to be products. So a lot of times they are vented at different conditions. Vented just means that when they're collected, they're cooled down, or they're heated up, depending on the conditions that would be in chemistry too. So we have two different conditions now. And here's the same equation. That the question's not all moving with it. And again, I must have thought this was a lot of fun because I keep having to balance it again. Now the reaction takes place. So on this side, I'm going to say this side is 45 degrees. Well, why would I even do that? 318 Kelvin and 745 torr. And on this side, it is, do it quicker, 75 plus 273 is 348 Kelvin and 655 torr. I like to write them down so that I know which way I'm going. Now, how many liters of oxygen, so here is my desired, are required to produce 14.5 liters of carbon dioxide. So this is our given. Okay, so we're going to turn our given into moles. And again, N equals PV over RT. So I'm going to take, and now my given is on this side. So I'm going to use these conditions. So pressure is going to be 655 times the volume, which is 14.5, over, it's in torr still, so 62.396, times temperature, which is 348, times desired over given. That just turned it into moles. I still have to do desired over given. 5 over 3. And now that gives me moles of my desired, and I want volume. So volume equals nRT over P. So I already have the N. This is all the N right here, so times the R, still 62.396, times the temperature. Now I'm over here, times 318, divided by the pressure, 745, and that will give me my answer. Now I can shorten it just a little bit because I do have the gas constant is going to cancel out. None of the rest of it will cancel out because I have different conditions, but I can take that out. If you forget and you put it in, it doesn't really matter. Your calculator will be kind and calculate it that way for you. So if I calculate this out, times 5 divided by 3 times 318 divided by 745, and I get my answer is 19.4 liters. So it's just not as quick as what the other is. When they're at the same conditions, I can just wipe everything out except for the volume and the desired over given. Everything else is wiped out. It will equal the volume. Here I just have to go through and calculate a little bit more. But as long as I have a calculator, it's not like I'm stuck doing this longhand. So it's not really all that more difficult. But that's how you would do it if you have different conditions. Now, an example so that you can see this, this is a very simple one, but it's also a very easy one to illustrate in the stoichiometry, so you can kind of see what's going on. If we take hydrogen and react it with oxygen gas, and fortunately this doesn't happen at room temperature. This is one of those that if you have it here, you've got to give it a bunch of energy. So this is a graph with the amount of energy on the side here. We have to give it a bunch of energy. You got to heat it up, give it a spark, something to happen. And then when you do that, then the energy goes way down. These atoms are much more stable as water than they are as individual elements. And how do we know that? Because when this happens, it gives off a lot of energy. All right, and in the hydrogen cars that they're trying to make, cars that run on hydrogen, if we can do that, if you can have a car that runs on just hydrogen, look at what your product is. What would be coming out of your exhaust pipe? Nothing but water. We probably would change from steel exhaust pipes, we'd probably go to like aluminum or something that won't rust, because if you just have just water running out all the time, then it's going to rust out. But if you have aluminum, it doesn't rust, no pollution, all you get is water. It would be completely clean. We aren't there yet. But we get a lot of energy out of it when that happens. Which is nice that we have to add this, what's called activation energy in. Otherwise, what little hydrogen is in the atmosphere, when it comes in contact with oxygen, it would just start exploding. We'd have fires all over the place, and that would be a little bit unnerving. Now, this can be dangerous. That's why we aren't driving hydrogen cars yet. So I'm going to let you watch a little clip on the Hindenburg, and this is the actual footage from 1937 when the Hindenburg, which was a dirigible, kind of like a blimp, came, and that's how they came. This one came from, I don't know if this one came from Germany. I almost think it came from Paris, but it came across the Atlantic Ocean on this big blimp, and then it landed in New Jersey, and you can see this in action and how much energy can be let out. You can also look on the tail of this because it is a German, which you would imagine, Hindenburg, sounds very German, and on the tail fins you will see the swastika. At that point, it's landing in the United States. People are gladly paying money to get on it, going over. Nazi Germany, the swastika has no stigma with it. It's just a symbol of a new, prosperous Germany that is burgeoning and coming along. This is 1937. World War II doesn't happen until later, a few years down the road. The United States doesn't get involved until like 1941, but it actually starts earlier than that. But it hasn't at this point, so the swastika is not a, ooh, why are they letting them land there? It's just like having the three-colored flag of Germany on there now. That's just a symbol of Germany. There wasn't anything with it. So go ahead and watch that, and then we'll come back and we'll talk about this a little bit more.
The ill-fated Hindenburg on her last flight sails over New York. These pictures, made from a Pathé News plane less than 4 hours before the tragedy, show the world's largest airship heading for Lakehurst, New Jersey. Over Newark's famous auto skyway, the airship was hailed by thousands who little dreamed it was their final glimpse of the Hindenburg. Inside the silver envelope are 16 separate gas bags, each filled with hydrogen, a highly inflammable gas. From the ground, you can see the forward control cabin from which the ship is operated. The windows along the side indicate the location of the passengers' quarters, in which many were carried to a flaming death. Approaching Lakehurst, the Hindenburg appeared a conquering giant of the skies, but she proved a puny plaything in the mighty grip of fate. It almost seemed as if fate had set the stage for the horrible tragedy. A graceful craft sailing serenely to her doom. For 3 hours, the dirigible circled the landing field at Lakehurst, New Jersey, dumping more water ballast than ever before in vain efforts to level off. Again she dumps ballast, and a nervous tension grips those who are watching, for this is something unusual. There goes more ballast, but the tale is settling in spite of all that has been dumped. A grim note of impending tragedy. Finally, the landing lines are dropped. These scenes were filmed by Pathé News cameraman William Deek, and you are about to see the pictures he got when the ship exploded. Those aboard leaping for life from a flaming inferno, the actual crash of the Hindenburg, an airship destroyed in less than half a minute. Rushing to the rescue, the heroes of the tragedy dash in, heedless of danger, to help the injured to safety, while others, beyond help, perish in the flames. The blazing aftermath reveals the extent of the disaster, an inferno which became a flaming tomb, a twisted mass of girders, the seared and scorched skeleton of what was once a mighty airship. The Hindenburg has gone. She represented man's latest attempt to conquer the Atlantic by air. Her tragedy will not halt the march of progress. From her ashes will arise the knowledge, from her fate the lesson that will lead to a greater and a better means of mastering the air. If so, her dead will not have died in vain.
Very famous clip, hard to watch knowing that there were a lot of people that lost their lives. A little bit more surprising is there's quite a few of the passengers that survived. I don't know how they got them out. I don't know how they made it down. It looks like the whole thing is in flames by the time it hits the ground. And they think that somewhere along the line, either just static in the air, something was a spark, there was a small rip somewhere in the fabric, and that's all it took. Now it burned slowly. I know it didn't look slow because there's a huge blimp in less than 30 seconds the blimp is all gone. Now it's still burning, but it's hot enough that the frame inside is actually caught on fire and it's burning the ground underneath. But the actual hydrogen is burned up very quickly, but it doesn't explode, it just burns. And when it just burns, that means that you've got, let's say, and this will be another demonstration I do for you. If you have a balloon and it's got hydrogen gas inside, and if we were to be silly enough to put a flame right there, it's going to melt the rubber, and right here, it's not going to burn in here. Why can't it burn in here? That's right, there's no oxygen inside here. This is just hydrogen. You've got to have oxygen for it to burn. So when it comes out here, there's oxygen. Should do that, make it a little different. I've got oxygen out here, so when it matches, hits the hydrogen coming out, I get a flame that comes out here. And I can get this, as this disappears, I can get flame all the way around. And if you do it right, it looks like, ooh, that exploded. It really just burns really fast, okay? And so we're going to watch. I'm going to burn a couple of these. It will even be a little bit of my, not only Mr. Thompson gets a soapbox, I'm going to get on my soapbox, the anti-smoking league as well here, and vaping as well. So that will be the added part to it. But you're going to get to see a burn like this. So let's go ahead and watch a few balloons go up. All right, I'm going to fill up the balloons with some hydrogen. Attempt to tie it off. And put it on a string. Here, and we know that the only gas that is lighter, less dense than helium, is hydrogen. So put that there. I will get rid of this. As mentioned before, unfortunately, this individual is a smoker. Bad things happen when you smoke. Okay, for the first time, I will do it with the lights on so you can kind of see what's going on. You need a light? I'll give you a light. All right, fireball, and kind of concussive, but not really an explosion. All right, we'll try it once with the lights out, and the sun is up, and so it's kind of bright in here anyway, but it is darker than the first one was. The flame. All right, now those were impressive, and they're large, but they didn't really, it sounded like they, you can actually even, sometimes, and I'm actually filming this before I've actually blown the balloons up, so it's a little bit of a Back to the Future thing here. Sometimes if it's big enough, there's enough of a concussion that it will actually make the blind shimmer a little bit. Even if it does, when I do that, I don't know if you'll be able to pick it up on the video, but if you were here in class, sometimes you can do that. You can actually feel it sometimes. That's not really so much from just an explosion. There is a little bit of a concussion, a little bit of an explosion when it goes up, but we're heating this gas very quickly. It's right now at about 20-something degrees Celsius. That doesn't tell me, but it's about 23 degrees Celsius, and once it catches on fire, heats it up a lot more, so it's going to expand very quickly. And when it expands very quickly, it sends out a shock wave, and that's what we feel the blinds get moved by. Now, if we were to figure this out, how many milliliters, because we're going to talk about small amounts here, and as long as we go through and we're using moles, and if we're using all of the R's and the P's and the T's, we've got to change everything into liters. But we're not going to, because all of those are going to cancel out. And we're just going to have milliliters times desired over given. It's just going to give us milliliters. So you don't have to change it to liters. And the amounts we're going to make, it's going to make more sense with the size that we have. How many milliliters of oxygen are required to react with 15 milliliters of hydrogen? Okay, so our equation again, H2 plus O2 will produce H2O, and 2 there, 2 there. So this is our given. So we have 15 milliliters, and since it's the same conditions times, I'm going to go to oxygen to 1 over 2 equals 7.5 milliliters. I only need half as much oxygen to make a complete quick reaction. That's the fastest reaction you can have when you have twice as much of this as this, and you add that little bit of activation energy, then you're going to get a big reaction. Larger reaction than what you saw with that. Now, the reaction we're going to do is going to be probably smaller in proportion, but probably more explosive. You're going to be able to see that, yeah, that was a more dramatic reaction. So that's exactly what we just did. So if we have an egg, which I do have an egg, should have had it over here. Here's an egg, and it's got a hole on the top and a hole on the bottom, and the inside is empty. You'll get to see the glamorous side of being a chemistry teacher when and how you can actually make one of these yourself later on in the video. But for right now, it's just an egg that has a hole in the top and the bottom, and it's just filled with air. All right, I'm going to fill it with hydrogen. And when it's completely filled with hydrogen, I'm going to take and be silly enough, I'm going to light the top of it. Now nothing, hopefully, I will wear safety goggles because sometimes it is chemistry, it's science, things can go poorly in it, but usually it's going to do a little puff and you might not even be able to see the flame, but the flame will be there, and it's burning because as hydrogen is coming out this way, it's meeting oxygen there, and it's actually producing water that you will not see because it's water vapor, and just little bits of it that goes into the air. All right, but the whole time it's doing this, oxygen is going up here. Remember I said there's a hole down here at the bottom, and as it's doing that, it's drawing oxygen inside. Now nothing can burn inside the egg because there's no oxygen here, but now we're getting oxygen. And it's going to just keep doing this, being a friendly little candle-like. You might not even be able to see it until we get to that magic twice as much hydrogen as there is oxygen. And it takes a little bit longer than what you might think because most of what's coming in is nitrogen. Most of what we breathe, the air around us, 78%, let's say 80% is nitrogen. So it's going to take a little longer. We're going to have some nitrogen in here too until we get that magic proportion of 2 to 1, and then all of a sudden that flame isn't going to be out here. It's going to go back down inside because now it's got the magic stoichiometry, and hopefully some dramatic reactions happen with that. So let's take a look and see how that goes. Well, I thought a little career instruction was in order. I know you guys all kind of envy the power and authority that a chemistry teacher holds, and it seems like such a glamorous position. Before you go signing up for education classes in college, let me show you a little bit how to get ready for the stoichiometry demonstrations. This is a regular egg. I used a drywall screw to, actually a deck screw, to make a small hole in both sides, and then I need to empty it. And they don't teach you this in teacher's education either. Ooh, we haven't got to the mother lode yet. Oh, we got stuck. Yep, this is what it's all about. Along with the glory comes the gory. Oh, so it's kind of a plug. Oh, there we go, there we go, there we go. It's good parenting classes here. Your kids will have a stuffy nose sometime. That's how she's done. So, it's more than just a get-rich-fast scheme. It's also glamorous. This time, we're going to use the egg, and I'm going to fill the egg with hydrogen. All right. And then I will put the hydrogen tank away, put the egg here, and hopefully watch what happens. All right, it didn't look like anything was happening, but as the ratio inside the egg, as it burned on top and it kept drawing oxygen in, it finally went to the point where there were 2 parts hydrogen for every part oxygen, and then the flame could go back down in and had a little bit more of a enthusiastic burn. We'll try this again. All right, same reaction. I have one more left. This one has larger holes, and you guys are lucky you're not here right now because it doesn't smell very good in here. I had to heat the ends of it because they're fresh. I usually like to let them sit for a couple of days to dry out, and then there's that membrane on the inside of an egg, and you can just kind of drill it out, and that otherwise it just flaps back over and doesn't let any air in as it's burning on top, and so nothing happens. So I had to dry that out. So this smells kind of like burning hair, except a lot worse. That same family. This does have larger holes in it, so it could go a whole lot faster. Alrighty then.